Good morning, my YouTube viewers. This video is going to be about experimental design again, and what we're going to be talking about is randomized block design. And in randomized block design, units are grouped into blocks based on known characteristics, and treatment is randomized within each block to account for variability between blocks. So we've got a practice question that we're going to go over to demonstrate randomized block design. And the practice question is, a researcher wants to determine whether 3 different fertilizers lead to differing crop yields. A researcher, since the soil quality varies across the field, they decide to block the field into areas of similar soil quality. How should the experiment be designed to test the effect of the fertilizers while accounting for soil variability? So we're going to answer that question by writing a program in Python. And in order to write the program in Python, the first thing that we need to do is we need to import the libraries that we're going to use to execute the program. So the first library we're going to import is NumPy as NP, which is a numeric library that also creates NumPy arrays. The second library that we're going to import is Pandas SPD, which is a data processing library, and it also creates data frames and series. The third library that we're going to import is matplotlib.pyplot as PLT, and that's a visualization library. And from scipy.stats, we're going to import F1way. So scipy is Python's scientific library. Stats is a statistical module within scipy. And F1way is an ANOVA. It's an ANOVA test that we're going to be performing. So we're going to simulate the data for the randomized block design. And the first thing we're going to do is we're going to set our seed. The reason why you set your seed is so whenever you run the program, it will initialize the variables to the same values, and the program will be run the same every time. So you set your seed by typing np.random.seed brackets 42. Now we've got to define our blocks or soil qualities and treatments or fertilizers. So soil blocks is a list of 3 elements called high quality, medium quality, and low quality. And fertilizers is a list of 3 elements called fertilizer A, fertilizer B, and fertilizer C. So we're going to simulate crop yields, quintiles per hectare. Okay, and so this is going to encompass 2 for loops. So data is an empty array or a list, because in Python there's no distinction between a list and an array, because Python doesn't have an array, it has a list. So there's no distinction between a list and array in Python. So for block and soil blocks, that's your first for loop. And for fertilizer and fertilizers, that's your second for loop. And then base yield varies by soil quality. Base yield equals, and you've got a dictionary, high quality : 80, medium quality : 60, low quality : 40. And then that's your block. And then the fertilizer effect varies slightly. So fertilizer effect is another dictionary. So fertilizer A : 10, fertilizer B : 15, fertilizer C : 12, and that's fertilizer. Then we have your random variability. Variability equals np.random.normal brackets 0, 5, 10. So it says you have 10 plots per combination. So what that means is you have a normal distribution, you have a mean of 0, a standard deviation of 5, and you have 10 samples. And then you have your total yield. Yields equals base yield plus fertilizer effect plus variability. And then you have another for loop for yield value in yields. Data.append block, comma, fertilizer, comma, value yield. And so that's your data. So you've got a list that's got block, fertilizer, and value, yield value. So now we're going to create a data frame that it houses all this information. So df equals pd, data frame, brackets, data, comma, columns equals soil block, comma, fertilizer, comma, yield. So soil block is your column number 0 or first column, and then fertilizer is your second column or 1, and yield is your third column or 2. And the reason why that is because in Python the numbering system starts with 0. So now we calculate the average yield for each combination. Summary equals df.groupby, brackets, square brackets, soil block, comma, fertilizer, and then you've got another square brackets, yield dot mean dot unstack. So now we're going to print the summary statistics, which we're going to print mean crop yields, quintiles per hectare. And then so we're going to come over here to the bottom of the cell. So mean crop yields, quintiles per hectare. So you've got your fertilizer, fertilizer A, fertilizer B, fertilizer C. Then you've got your soil block, which is high quality, low quality, medium quality. And then so it gives you the data for fertilizer A, fertilizer B, and fertilizer C. So we're going to go back up to the code. And we're going to perform an ANOVA. And in this ANOVA, it's going to be another for loop. The ANOVA results is going to be a dictionary. So for block in soil blocks, block data equals df, square brackets, df, square brackets, soil block is equal to block, and df fertilizer is equal to fert, square brackets, yield for fert and fertilizers. So basically we've got a second for loop, we've got a Pythonic for loop. And then now on this information, we're going to perform an ANOVA on this information. So fstat, comma, p-value equals f1 way block, and then asterisk block data. And ANOVA results block equals, and it's going to be a dictionary, f statistic colon fstat, comma, p-value colon p-value. And we're going to print the ANOVA results. So we're going to print ANOVA results by soil block, and then another for loop. For block, comma, results in ANOVA results, print f block colon f statistic equals results, comma, p-value. So you're going to print your f statistics and your p-value. And so come over here to the bottom of the cell, and your ANOVA results in the cell. So high quality, you have an F statistic of 0.373 and a p-value of 0.692. So that means in that instance, the null hypothesis would be accepted. So there's no significant difference among fertilizers in this group. In the medium quality, the F statistic is 3.753, but the p-value is 0.036. The p-value is less than 0.5, so that means that the null hypothesis would be rejected and the alternate hypothesis would be accepted. So there's a significant difference among fertilizers in this group. And low quality, the F statistic is 2.226 and the p-value is 0.127. So it is greater than 0.05. So that means that the null hypothesis will be accepted. And it says there's no significant difference among fertilizers in this group. So in this particular question, the reason why you have the 4 loops is because you're printing off different ANOVA for different circumstances. You've got ANOVA for high quality, medium quality, and low quality. And as you can see, the F checking whether the p-value is less than 0.05 falls within the for loop. So you can see that in the test that we did, you had 2 instances where the null hypothesis was accepted and 1 instance where the null hypothesis was rejected. So now what we're going to do is we're going to visualize our data. So plt.figure brackets fig size equals 6, 4, and then you're going to say for I, block and enumerate soil blocks, 1, plt.subplot brackets 1, 3, I, and block means equals df, square brackets df soil block equal to block dot group by brackets fertilizer square brackets yield dot mean. Block means dot plot, and it's going to be a bar chart. So brackets kind equals bar, color equals blue, orange, green, alpha equals 0.8. The title is crop yields and block. The X label is fertilizer, and then I rotated the X ticks by 45 degrees. The Y label is average yield. The Y limb is 0 to 110, and the grid is axis equals Y, line style equals dash, alpha equals 0.7. So plt.type layout and plt.show. So you can see these are the graphs that we made, crop yields in high quality, medium quality, and low quality. And then it gives you the average yield for high, medium, and low. And then it gives you the fertilizers. So in high quality and low quality, you had the null hypothesis was accepted, which means there's no significant difference between the means of the groups. But in the medium quality, the null hypothesis was rejected, and they said that there is a significant difference between the group. But looking at the chart, it doesn't look that significant to me. But obviously, this is a data-driven exercise, and so since the value was less than 0.05, we had to accept the alternate hypothesis and reject the null hypothesis. So that concludes this video. The next video is going to be on another experimental design, so I hope that you decide to watch it.